So last time we started to talk about how we can find or draw the maximum, the shear diagram, moment diagram, find where is the maximum shear happen, where the maximum moment happen. And now that's when we have a beam, we are given and we know how the moment change in the beam, where is the maximum. Now we want to know how can design that beam. How can design that beam that doesn't fail under that moment. So design the beam. Remember, up to this point, we already learned how to design beam, make sure it's not failing under the axial load. Then learn how to design the member to make sure it's not fail under the torsion. Now want to make sure you're designing the member does not fail under the bend. So if we want to make sure that's not fail under the bending, basically we have to calculate the stress and make sure the stress happen under the bending is less than what the beam can handle, correct? So the stress under the bending, what was the stress under the bending? The sigma was MC ion, correct? Remember that? It was an MC divided by I. Usually in the design purpose, we are not writing it like that. We are going to rewrite it as, I'll tell you what, we're going to rewrite it as M divided I by C. Usually write it like this. So bring the C down. The thing is that this part, this is S. So usually we write it as M divided by S. This is how usually we write the equation of that. So if I want to find the sigma max, so what's the maximum there? So if I go and say, okay, what's the sigma max? This is what we are looking for. So sigma max happens where it happens where the M become max, and the M, it doesn't matter. We are looking for the absolute value of that, where the M is max. So we are going to say that wherever the absolute value of the M is max, sigma max happen there divided by S. Agree? So this is the maximum that can happen in the beam. Now, what's the maximum we can tolerate, can handle? The sigma allowable. What was the sigma ultimate divided by factor of safety? Correct? So that is maximum we can have, that's maximum we can handle. So basically that's maximum we have, that's maximum we can handle. So basically we have to say that sigma max have to say that the sigma max should be equal or less than the sigma allowable. In other words, I'm going to say that the sigma allowable should be equal or less than, I'm going to just write equal of the M max divided by S. That S is the minimum allowable S. That's the smallest cross-section allowed. Okay, so that's it. And so basically what I want is that, and I want to calculate, so I want to say that the S mean is gonna be the M max divided by sigma log. So this is the cross section I'm gonna use. So I want a cross section that is S is larger than that. Question up to you. So in a simple form, I will calculate the sigma max, and then I make sure it's going to be less than whatever I'm allowed, and from that I will find the S. So what's the steps to design the beam? So if I want to put it in some steps. The steps to design a beam for bending. So the first step that I want to design a beam, what would be the very first step?
Probably know what either the factor of safety is or what material we have.
That's it. The first thing is that find out what material we want to use. So is it going to be the steel beam? It's going to be the concrete? It's going to be wood? Whatever material is that. So the very first thing is that we have to determine the sigma allowed. So the first step is determine material to use and find sigma allowable. So what's the allowable sigma that we have equal to sigma u divided by Fs. So basically we said, okay, this is the material we have, this is the factor of safety we want to use for that specific material or that specific project. And so we find the sigma allowable. So that's the very first thing that we want to find. The second thing that we want to, okay, after we know that what's the sigma allowable, we have to find the maximum load applied on that. So maximum moment applied on that. So the next step is that draw shear and moment diagram and find maximum moment in the beam.
So are we treating it as if it is a rectangle and we're just trying to figure out what height and width to use? Or is that like is the shape of it the next step?
The shape of it comes from that. But we find the S, and then depending on what type of shape we have, we
Okay.
calculate S for that specific type of shape. So now that we have these two, we have the allowable shear and we have this maximum, then what we can find is that we can go there and find the S mean, correct? So we can go there and calculate S mean, which is equal to M max divided by sigma allowed. So now that we know that this is the minimum S that our cross section should have. Now it comes to your question. Now that we know the S, how we are going to find the cross section itself. So there are a couple of ways of you doing that. For most of the steel beam, if you look at the book, you go to the very back of the book, Appendix E, there's a table there that it gives you there's tables for different type of steel beams. And those steel beams, I will go through them, so they have the shape of the dimension of the beam, and then they have the width, the thickness, all dimensions, and then they have the moment of inertia, and then they have the S. And then you go there and you look at the S and you find the S that is larger than that. That's going to be your steel beam. So if you are dealing with a steel beam, you go to these tables, locate the S, and go until you get to the S. For example, if you calculate the S is 100, you go there and find the one that is just above 100. That's going to be your beam.
So they're all going to be, for the most part, I-beams if we're dealing with metal?
They can be I-beams, they can be L-beams, they can be wide all beams, they can be look like U-shape.
But we won't have to deal with that shape. It will have like a reference of what shape to use for the material.
In this, for example, it's the L shape. So here, in the strength of material, they will tell you, okay, that's what type of beam you want to use. So they tell you, okay, you will have the I-beam, L shape, whatever. But when you get to the higher level design course, usually you also have to find out which one is more proper for which one is best suit for the project you're working on that. But these are for very high level course. For now, mostly they want you to say, if you are given the beam, you can find which one is going to be handled that moment. So if this is the I shape or the steel beams, you use the beam table. So for steel beam, use the beam table to find cross section or to select the cross section. With S is larger. If you have the rectangular beam, for steel beam is like that. For rectangular beam. Usually for rectangular beam is gonna be concrete or wood or something that has cross section of rectangular beam. S is I divided by C, correct? So for the rectangular is 1/12 of BH3 and the C is half of the H. So for the rectangular beam, the S would be 1/6 of BH squared. So you have a rectangular, it's gonna be BH. So I have a rectangular beam, you just use that equation to find the dimension. If you have a steel beam, you use the tables at the end of the book to find the cross section. So, any question up to here? So you know what's the steps to do? I'm gonna do some examples, show you how to do that, but any question about the steps, how we are doing that? So let's look at a couple of examples. Remember that this sigma allowable, some material might be different. Some for steel, in the compression and tension, they have the same sigma allowable. But in some material like the concrete, the sigma compression and tension are different. So you have to find both of them. You have to design it or check it for both compression and tension if the material behave differently under the tension and compression. Remember that. Here, what we are gonna, everything that we deal with is gonna be the same. Then, if you have the material that behave under the compression and tension differently, once you have to find the maximum M for the compression, once you have to find the maximum for the tension. So remember that. Here we are not dealing with that, but in real world, for example, the concrete is one of the examples. The concrete in the compression and tension behave differently, so you are doing this 2 times. Once for the compression, once for the tension. So assume we have a beam like this. Let's say A, B, this is 8 foot, and there's a 15,000 pound applying on the end of that. So 15,000 pounds applying on the end. So I want to design that for if it says if the sigma the so this is a steel and it says that if the sigma allowable is 24 KSI, then find wide flange or design fine flange. So we want to find a wide flange beam made of steel that can handle that load. So if you want to look at the sigma level is already given. So the first step is already done. We don't need to do much about it. Correct? So we have. So want to go through them. Sigma level is 24. Now I want the M max. How much is the M max? In more complicated case, I have to draw the shear and bending diagram. We will do that. I will show you about that. But it's a simple case. Where would be the maximum moment happen in that beam?
Near the bending.
Right at the B.
Yeah.
Right? So the maximum bending right happen here at the B. So if I calculate the moment at the B, it's going to be my maximum. So it's going to the maximum bending is going to be the moment at the B, which how much is the moment at the B? 15k times 8 feet. So it's got a 15.
120.
8. It's 120. Let's do this. Because we needed to have it in inch, because this is an inch.
Okay.
So let's make it times 8 times 12.
1,440.
40. So that's the maximum moment that we're going to have in Gibbs inch. So that's this is converting foot to inch. So the next step is that I have to find the S mean. So sigma it's gonna be the I usually myself is my preference to write it like this because this is a form that my eye is familiar with. But if you start to write it like that, that's okay. So therefore I have the 24 is equal to M max, which is 4D, 4D, and then the S mean. Therefore the S mean, the minimum S I can have is 60 inch cubed. Okay, so I know that I need a wide flange beam with the S 60 or large.
It has to be either equal to or larger.
Yeah, it should be, because this is the minimum S I can have. So whatever I'm gonna pick, look at here, the S should be equal or larger than S max. So I have to go back to the back of the book and start to looking into those tables to see which one fits. And
The closest one we have is a S of 62.6.
make sure they're using the foot inch.
Yeah, it's in inches cubed already.
So look at here, Usually the wide flange is written like that. For example, devil, I'm gonna write one of them. Usually it's like that. It's the W. When it's W, it means the wide flange. And then it's gonna be the height. Is that correct? It's the height multiplied by weight. The unit weight, I would say. So it's usually written like that. The number you see. So usually you will go after the one that has the smallest unit weight, because you want to make it as less heavy as possible. So there are many possibilities there that the S is 60 or less, but if you look at the table, the one that probably have to go after is 16, W 16 by 40. Go ahead and find the W 16 by 40.
16 by 40.
Yeah, look at here, it's a W.
Oh, okay.
It's a W 16.
Yeah, I see that.
And then multiply, then it's multiply 77, 57, 40. So 16 by 40.
16 by 40. That's like 60 by 40.
So if you go and find the S for 16 by 40, how much is the S for that?
64.7.
So it's very close to that.
Yeah.
So that's the one they're gonna pick.
So how come we didn't choose one that's closer even? There's one that is 62
But
points.
how heavy it is? It's very heavy. Look at that.
Oh, okay. 24. W14 times 38. I mean times 40.
So that's the 43.
Yeah.
See? So it's heavier than the previous one. So what we want to do, we want to have the lightest one that can handle that force.
Okay.
So the other one that has it is 43, this one that has it is 40. So there are many options there. If you go there, you can find it. So you find the one that has the S minimum and has the smallest unit weight. That can handle. So we're going to then use for this specific problem. So that'll be 16 by 40. That will be 16 by 40. Question? I'm going to look at one or two more examples, but that's basically the process of, or the steps of designing the beam. wooden beam, okay, like this. That's gonna be at the A and the B. It's gonna be 8 foot. It's gonna be 4 foot. And has a cross section of, is a wooden beam, so it has cross section of 3.5 inch. You know that's the width, and then we want to find the height. So the load on that, 400 is the load. And 400 pound per foot, and then we have 4.5 keeps. And the allowable stress is 1.75. The sigma allowable is 1.75. Yes. So basically is that the ship will go to buy a timber, that's a 4-inch timber. And say, okay, what would the height I need to make sure that's gonna support that. So the very first step is that I have to draw the shear and moment diagram. To do that, I need to find the reaction of the support. I'm not gonna do, I'll just put the numbers there, but have to calculate them basically if you want. So the reaction of support is if I want to go there, so it's negative 0.65 and this one's at 8.35. So these are the reaction of the support.
In what units?
This keeps same as there. So now I want to go ahead and start drawing the shear and the moment diagram for them. There's the shear and then the moment. If I bring these ends down. So if I start for the shear, so the concentration load negative 65, so I have to start from negative 65.
That's 0.65.
Yeah, 0.65, yeah, negative 0.65. So that's where I started, but I pushed it down. And then I have the distributed load that is also pushing it down. It's constant, so it's gonna push it down linearly. So the amount of that is 400 times 8.
And then won't we have to put it into inches? Because it's kills. And 8 is feet.
So yeah, so it goes something like this. So when it gets there, it's gonna be equal to negative 0.65 times 10 to 3 minus that amount, minus 400 times 8, which would be, what's that? I think about 3850. It's about 3850, negative 3850 pounds. Which would be negative 3.85 kips. Then it gets negative 3.85 and then 8.35, pushing it up. So it's gonna go to, how much gonna be? It goes up to somewhere here. So negative 3.85 plus 8.35, 4.5.
Yeah.
Plus 8.35 is gonna be 4.5. And then it's gonna stay constant there. It gets to the concentrated load will be pushed down to 0. Now I want to draw the moment diagram, so before I start it, I need these two areas. So what's the area here?
That's gonna be fun to do.
Should become negative 18 keeps foot. Is it right? This one is plus 8. If you have all the numbers correct, it should come out to negative 18.
It's just a pain in the butt because it's not just a triangle. It's like.
Yeah, you have to find these. You can either use the trapezoid equation or use the square and the triangle, add them together. now for the moment, so the moment I know here it's gonna be 0 because it's the simple support at the end, so it's gonna be 0. Then the area here is negative, so it's going down. And it's linear, so it's gonna be power of 2. So it's going down with power of 2 like that. And how much is gonna be there? So it's gonna be 0 minus 18, correct? So it's gonna be, this point is gonna be 0 minus 18 would be 18 cubes foot. From here to here, from here to here. So positive, so it's going down or going up, because it's positive, so it moves up. And then it's constant, so it's gonna be linear. Because it's constant, so that would be linear. It goes linearly from here to 0. So that's gonna be negative 18 plus 18 would be 0. So now that I know the maximum moment, which is going to be 18,000 pound foot. So if I want to, so I will go ahead and write that the sigma allowable is equal to M max divided by S mean. Therefore, I know 1.75 should be equal to maximum M, which is gonna be, where that's, it's gonna be 18,000 times 12. Why times 12?
Because the one equation is to the 112.
Not 18,000, because we have that in the KSI is also, so we just keep it 18. So it's going to be 18 times 12 multiply 12, because this is in pound per inch. This thing is pound per inch, so I make sure that this is going to be in inch. So that's going to be foot into inch, and this is gonna be the keeps foot, and then this the S mean. Therefore, the S mean would be equal to. If we have everything correct, comes out to 123.43. So that's the S mean. Now I want to find the S for that. So what was the S for the rectangle? 1/6 of B
BH cubed.
BH squared.
Squared.
Correct? And it should be equal or larger than the S mean. So therefore, 1/6 of the V is 3.5 inch multiplied by the H cube should be larger or equal to 123.43. So therefore the H should be equal or larger than, I got 14 something here, yeah?
Yeah.
14.546 inch. So the H I'm choosing should be larger than that number. So usually, if you see that part is the part that is take more time, and you have to make sure you don't make mistake. This part is relatively straightforward. The last example for the beam. Here, 50 kilonewton, 20 kilonewton per, probably per meter, and it's going to be 311. 3 meter, 1, it's point A, it's point D. I want to sigma allowable is for the steel is 160 megapascal. And want to know the Y flange. That's it. Y flange. So again, the very first step, you have to find the maximum moment there. To do that, you have to find the reaction of the support. For at A, the book has the detail of how to calculate it. It's 52 kilonewton, and for the D is 58 kilonewton. Going up, both of them positive. Now we want to look at the shear and moment diagram for them. So for the shear, and for the moment, that's X, that's X. So for the shear, it starts, it's going up 52, so we know that's going up, pushing it up concentrated to plus 52. And then is the linear distributed load, so it's pushing it down, and the entire thing goes down to here. It's gonna be 52 minus that area, which is gonna be 20 times 3. So it's gonna be negative 8.
Yeah.
Negative 8. And then between these 2 points, it does stay constant, nothing happens. Then again, it pushing down, need 50 more. So it's going down to so it's negative 8 minus 50, so it's got a negative 58. then it's going again. Nothing happened between these two, and then 58 up. That's a negative 58 plus 58 goes back to 0. Negative 58 plus 58 is 0. Then I need to find the area underneath of each of them. Area here is going to be plus 67.6. Area here is negative 1.6. That is negative 8 and negative, so that's negative 8, negative 58. So now that I have them, I can go ahead and draw the moment. So for this part, it's a linear, it's a positive, so to this point, I need to bring down this point as well. Up to this point is going up. Go there. And linearly goes there. Linearly goes there. So I know that it's gonna be 0 at the beginning and 0 at the end. And this point is gonna be 0 plus, so it's gonna be 0 plus 67.6, which is gonna be 67.6. Then here, gonna be 67.6 minus 1.6. That's 66. Then here is gonna be 66. And then here is the 66 minus 8, which is 58. And here is the 58 minus 58, would be 0. So again, the maximum shear, the maximum moment I have is 67. 0.6. So the rest again is similar like that. The sigma allowable is gonna be the M max divided by S mean. So therefore, it's 100. It's 160 megapascal. 160 megapascal is equal to the M, which is 67.6 times 10 by 3 divided by S mean. So the S mean would be equal to 422.5 times 10 to negative 6. meter cubed, or because everything is in millimeter, it's 422.5 times 10 to the third millimeter. So if you go back again to those tables at the back of the book and look at the table, the one that has that is going to be the W360 times 32.9. Look at the table, look up the table.
Where are you, what page is that? Cause like, right now I'm only seeing the US units, like inches and whatnot.
Is one side is US, the back of that is SD.
Oh, okay, oh, yeah, found it. Cool.
Says it. Just have a page number.
It's 822.
Eight.
That's, it's like that, it's like a very nice one.
So if you look at that, the S for that is 475, which is gonna be a little bit more than that 422. Any question? So that's basically how we designed the beam for the bend. Remember that when you are designing a member, you have to design it for all the forces applying on that. If it's the pure bending, only we care about the bending, that's what we are gonna get. Again, when we get to the design courses, they will go in details of how you are gonna pick that. How you're gonna pick that, why you're choosing the I-beam, or for example, why this type of material. So you will go through that part in detail in the design course. This part is the important part of the strength of material, that you can find the minimum. So we're moving to the next chapter. So that's the bending part. So we talked about it to here. So up to here we talked about if you have a beam and it's gonna be under axial load. So it says that, okay, how we are gonna design it. Correct? So the axial load. Then after axial load, we went and talked about what if we have a member that is under torsion. Then we're gonna go ahead and say, then we have and the beam that's gonna be under bending. So we have these three up to here. So there's how to design axial load, how to design torsion, how to design the bending, and the very last one that's left that we have to design a member for that or check the member for that is, you know, what is it? The last one, if you cut the butter,
Shear.
shear. So we want to make sure that it's not like the it's not like the butter that we put the force on top of that member and that member is gonna put, like the butter is gonna cut through that. It's gonna be shear. So basically in this step I want to see the shear, the stress. So we have the first three, and now we want to look at the remember that under the pure bending, so there is no shear in beam under pure bending. So if there's a pure bending, there's no shear applying on that. So for example here, if I go ahead and cut part of that or part of that, if I have it here, and then I have it here. So here I have the moment, and here I have the force. If I look at the internal forces there, so the internal forces that I would have is going to be the P, the V, and the M, and the same here, V, P, and the M. So here, for this case, V is 0, P also is 0. But for this case, P is 0, but V is not 0. So that's the difference between these two. So here, there's no shear, here there is a shear.
Would there be a moment?
There would be a moment in both of them. So here, M is not 0. Here, M would not 0 as well. So here you don't have a shear, here you do have a shear. Anyway, so if I have three pieces of three pieces of sheets are sitting like this on top of each other.
They're touching, right?
Yeah, they're touching.
Okay.
And then I'm gonna make two things. One time I'm gonna bend it one time, I'm gonna put the force on that. So I'm gonna bend them once with the moment, once with the force. If I consider these 2 points in one of them, assume here, it is A, and underneath the same one underneath is gonna be A prime. Look at here, if I bend these pages, you see the edge, how they like slip on top of each other. So if they are here and I bend them, they start to slip and basically they get a distance from each other. So that's what would happen there. So if I bend them, if I purely bend them, what would happen is that these 3 would be goes, the first one will goes like this. And then the second one will go like this. And the third one will go like this. So there would be, if I bend them, if I put a bending moment on the end of them, that's what happened. That point A and the point A prime will stay exactly on top of each other. So if this is A, and this is the A prime, they stay on top of each other, exactly on top of each other like they were at the beginning. But if I go ahead and instead of bending them, I put the shear on them, I put the transverse load on them, so if this is the first one that happened to look like this, the second one will go like this. And the third one will become like, so it comes up to here. It becomes like this. If I put the force on the top, if I put the F here. In this case, when I put it like that, then what would happen is that
A and A prime will no longer be in line with each other. Like
no, then the A would be, I'm exaggerating, the A would be here, and the A prime would be here. So no more, so you see, they move in the horizontal plane, horizontally where they were. So my point is that, look at it, if I have a force, the shear force, I have a shear vertically, correct? But look at these 2 points. These 2 points are moving away from each other. What does it show? So they are also a horizontal shear force. Because these 2 plates, when I have them and I bend them, they move on top of each other. So why they move on top of each other? There should be a horizontal force to make them move. So under bending, there's nothing happen horizontally. But under the shear, under the transverse load, there would be both vertical and horizontal shear. How to calculate it, I will tell you later, but did you get the concept of that, why there is a horizontal? The vertical is clear, you can see it. The vertical shear is clear, you just cut it, you can see it there, it's there. But the horizontal is like that. You can put a couple of sheets of paper and bending, and you will see those will slide on top of each other. Why they slide horizontally? Because there should be a force horizontally to make them slide on top of each other. So there should be a horizontal shear stress as well. So under transverse load, shear stress occurs. On both horizontal plane and on the vertical and on goes on horizontal and on vertical transverse plane. So the force is vertical, but the result gonna be both vertical and horizontal, the shear stress that it causes. That all I wanted from that example. It says that we have the vertical shear stress, but also we have the horizontal shear stress. And we are gonna look into them separately. Any question up to here? Now, we are gonna first look at the horizontal stress. It's a little bit more straightforward, so this is a bit easier than the vertical shear stress. So first thing, we are gonna see how we can calculate, how we can find the horizontal shear stress in the field. So once had a baseball player students, and we use the same. When we hit the ball with the baseball, with the what's that?
Bat.
The bat. When it breaks horizontally, the length of the bat, not perpendicular to the bat. And the reason is that the wood is much weaker in the horizontal plane rather than the vertical plane. And when that transverse force applied on the bat, you're gonna shear both on the cross section and on the lengths. Because it's weaker on the lengths, it's gonna break throughout the lengths of the bat. So horizontal shear stress in B. So if I have a beam, a simple beam like that, and there's going to be two forces applying here, and some distributed load applying here. Example of that beam. I'm going to make it now if I go ahead and say I'm gonna grab and look at a part of that is under the load. I'm gonna get this part and draw them large. I'm gonna magnify that part. So what I'm gonna have is that for that part, like this. Let's see how long I draw it. Make sure it's gonna fit there. So if I magnify that, there's going to be the load applying there on that part. And then I'm going to pick the element inside that and call it C prime, C, C prime, D prime. So I'm going to bring out an element inside that. So element here. Call that C. So it's going to be C, C prime, D, D prime. And now I'm going to draw that element and put forces on that. So if I draw that element, bring that element out, and put the forces on that. So I'd make it bigger here. So I bring out that element, make it larger. So it's good. Is it C, C prime, D, D prime. And I'm going to put the forces and stresses on that. So on the top, there's a distributed load on the top, correct? So there's a distributed load on the top. What would be on the sides? On the side would be the shear stress from the bending, correct? So there's going to be the shear stress. So I have the shear stress from the bending here. And I have the shear stress from the bending here as well. So I have shear stress on the, from the bending on the both sides. So it's going to be sigma at C, it's going to be sigma at D. Then I'm going to have the vertical shear forces. Right? So that would be the vertical shear forces. That's going to be the V prime at C and V prime at D. So if I have that, if I want that to be in equilibrium, what's missing?
Force coming up from the bottom.
Now assume that will be cancelled by these two. Unless these two are equal, the sigma C and sigma D, unless the sigma C and D are equal, which they are not, is not in equilibrium horizontally, correct? Because in horizontal, these two are not equal, so it's not in equilibrium. So how I'm going to make it in equilibrium, that I am going to have to put some force there and call it delta H. So I need some force here to balance the horizontal force for me. If this distance, if the length of the element, I call it the delta X, then Q is equal to delta H over delta X is going to be equal to VQ divided by I. V Q divided by Y. So, what's the Q? Q is called the shear flow. So it's called shear flow. And it is equal to horizontal the Q is a horizontal shear per unit length. Horizontal shear per unit length. Remember that it is horizontal, not the vertical. And it's going to be Newton per meter. So that's very important that you remember that it is horizontal shear. So that's the Q, the small q. The V is the vertical shear force moment of inertia. For my moment of inertia about centroid axis for entire cross section. The other ways makes it so it's a moment of inertia for entire cross section. About so that's the moment of inertia for entire cross section. About the axis passes through the center. And the Q, the big Q, capital letter Q is it. Is the first moment of, I'm going to show you this is the first moment of area is picked to neutral axis for area above or below the line we calculate Q for that. I'm gonna explain it what it is. So in that equation, if you look at this equation here, the internal vertical force, you already know how to calculate it. We did it many times. You draw the shear diagram, you find the shear at the cross section that you're asked. So that part is not, that part we have done it many times here in the statics. The V. The I, again, is the moment of inertia for a cross section. We practice it many times. The only one that needs to be calculated is, it's very simple to calculate, but a little bit confusing. So if you get it how to calculate it, relatively very simple. So that's the Q. So I'm gonna say how to find the Q. So, next things, so first I'm gonna tell you how to do the moment of area, and if you have a time, I show you the example of how to calculate it. So So we want to say how we can calculate the moment of area. Next. The moment of area, if you look at this equation, the Q is integration of y dA over the area. So it's the integration over area. But if you have a angular cross section, and then I'm gonna have neutral axis. Over here, so it's gonna be the neutral axis, and then assume this is the be the y, and then so this is the cross section. Assume I want to find a listen here. Assume I want to find the horizontal force at this level, for example, at this level. This is where I want to find the horizontal force. So it's a cross section. I want to find the horizontal force applying on that plane horizontally, like this, going like that. So if it is there, then I'm gonna divide that into two areas. The area above that and the area below that. So it's gonna be called, this area is gonna be either this area above that would be A, and the area below that is A prime. So the area above that line and area below that line. Okay. Now assume the distance to this line is y1. So assume this is y1. The distance to the line. If I go ahead and do the integration, if I calculate that integration, if I go ahead and say, and y dA, and you do the integration over the area of y dA, these two will become equal. So if I calculate the integration of y dA over A or over A prime, they will become equal. If I calculate that, just accept it. If I do the integration, they will be equal. Or in other words, the Q about A would be the Q for A prime. So the moment this Q, when I want to find the horizontal shear stress, I calculate the Q. I can calculate the Q for the above the line or below the line. That's the where I said that above or below, because they are both equal. It doesn't matter. I calculate the Q for the area above the line or the Q for the below the line. How to calculate it, I will tell you. But any question up to here?
Is that y the y1 or just y?
No, why?
Okay, sounds good.
Now, the point is that here, if y1 becomes 0, then Q is max. maximum. So the Q become maximum when the line or the surface I'm calculating the Q for be the neutral axis. So if that goes and happens to be there, that's the maximum Q that I'm gonna get. Now, if I have a cross section like this, I'm gonna draw that cross section again. If I have that cross section, and then I have the same neutral axis going there. And then I want to find the shear in that line there. If the distance of that, so if this is gonna be this distance up to here, so it's gonna be y bar, and this area is the A. Q for the A is the area of the A times y bar. So calculation is relatively simple. The area times y bar of that area. So first moment of area about an axis is equal to first moment of area about axis is equal to the product of area and the distance from its centroid axis. That's very, very quick. Simple example of how I can calculate that Q. So it's saying that if I have a cross section like this, a section like that is going to be 100 millimeter. It's going to be 20, 100, and 20. That's going to be 20 here. If I have a cross section like this and say this cross section is made of basically look like this. So we have three separate parts that actually they are nailed together like that. So they are nailed together. So there's a nail here. And there's another nail here, there's another nail here, there's another. So they're nailed together on the top and the bottom. And the same here, so there's a nail here. So these are nailed together, so these three pieces are nailed together, and the so we know that V is 500 Newton, so the vertical force of V is 500 Newton. And the nails, the distance between two nails are 25 centimeter. So spacing between nails is equal to 25 centimeters. So every 25 centimeter we have one nail. So we want to know shear force in each nail. So look at that. There's a shear force horizontally, correct? At the interface, there's a shear force there that apply at the interface. So this, listen here very quickly. The shear force applied at that plane, correct? There. So if I have that, that's where the shear strength happen, horizontally between the top and the middle, or the bottom and the middle. It's gonna cut it there. So I want to find the shear stress horizontally at that point. So it means that that red line is gonna be in the interface of the top and the bottom. So I have to find the here at that point. I want to find to see what happened there in that interface between the two. So the first thing I need to find is the Q. How much the Q for that top part? If I go ahead and say this is the A, if I say this is the A, so how much the Q for the A? Q for the A is the area of the A times Y bar. So the area of the A is how much? 100 times 20, correct? How much is the Y bar?
60.
So yeah, so the Y bar is from here to neutral axis, correct? So this is the neutral axis, and the centroid. That's the Y bar, which is 60 millimeter. Times 60. So how much is that?
12,000.
So it's gonna be 12,000. Millimeter cubed, or it's going to be 120 times 10 to negative 6 meter. I have it in the meter. The next thing is the I. I have to calculate the I for the entire cross section, for the top, for the middle, for the bottom. So remember that the I is sigma I about the centroid plus AD squared. So the I for the top one is 1/12 of 100 times 20 cubed, 1/12 of BH cubed, correct? And then plus the area, which is gonna be the 100 times 20 times the distance between the centroid and the axis. So that's the D, which is gonna be that 60 squared. For the middle part, because we did that, I'm gonna write it as 1/12 of the B is 20 times 100 cubed plus the area, which is 20 times 100. The distance of between its centroid and the neutral axis would be 0 because they're the same. And the bottom part is the same as the top part, so it's going to be 1/12 of 100 times 20 squared cubed plus 100 times 20 times 60 cubed. So if you have it, it's going to comes out as, I don't know how much the millimeter, but it would be 16.20 times 10 to negative 6 meter the 4. And then the Q is the VQ divided by I, so it's going to be 500 times the Q, which is 120 times 10 to negative 6. Divided by 1620 times 10 to negative 6, which would be 37.04 Newton per meter. So, listen very quickly here. The Q is the Newton per meter in which direction? It's the horizontal shear, correct? So it's cutting there. It's cutting these two, so it wants to cut it horizontally there, correct? So how much force would be applied on each nail?
Well, that's per meter, the nails are 25
So yeah, correct. So the Q is the force per length. Is the force per length. Therefore, the force would be 0.025 times. So it's going to be 92.6 Newton. It's going to be the force applying per nail. So each of the nail will get that. So very quickly, the only part that is this part. The rest, the I, we had it before, we did it many times. So this part, just define the interface that you want to find the shear stress at that interface, and then use this equation either for the top part or bottom part. If I write this equation for the bottom part, I will get the same answer. It's easier to write it for the top part. So write the interface, horizontal interface, right, times the area by the y, and it gives you the Q. The rest is relatively straightforward. So the equation is very simple. That Q is confusing. Any question?